Yes, now this is part 2, and this is where we actually get into, let's figure out, because we want to answer the question. What was the question? How long does it take to heat my still? Well, in actuality, that question should read, how long should it take to heat my still? Because that's going to give us the information, that data point we always talk about, that we need in order to determine so many other things. Yes. And this is, of course, I've got the formula written up here of volume in gallons times 8.33. You do that first, times final temp minus starting temp. And then the result of that would be divided by kilowatts times 3413. That will equal the time it takes. Let's simplify this. Okay, now for those of you who routinely shoot to the end of the video and look for the answer, we're going to give you the answer up front. We're going to do one real quick. And I'll do it like this. I'm going to use an example, which is going to be this 8-gallon still. And I'm going to say, for the sake of argument, we're going to use a 1 kilowatt, 1,000 watts. Okay, because a kilowatt is 1,000 of them. So we're going to use 1 kilowatt. So we're going to use a 1 kilowatt element. All right. We have 1 gallon of water. And we're going to raise that gallon of water by 100 degrees Fahrenheit. All right? And that's what we're going to do. I'm just going to do the problem real quick and show you how easy this really is. Now, for those who are, and I know I wish the whole world used the metric system, but they don't. All right? And I'm more familiar, more comfortable with our imperial system. So I use gallons and I use Fahrenheit. And if you're really, really concerned, you can work it out this way and convert everything on the other end. Or you can work your way through it, and we'll describe how to do that, of course. But so I'm using our imperial systems, and you can easily convert that. Here's an example. Alexa, convert 1 gallon to liters.
1 gallon is about 3.8 liters.
It's as easy as that, or just type it into your search bar. All right, so what we have 1 kilowatt, 1 gallon, and we're going to raise it 100 degrees Fahrenheit. How long should that take? Here. Oh yeah, I'll just write it out here. That's going to be 8.33, right? 8.33 times 100, and then we're going to divide that by 1 kilowatt, which is 3413. And that's going to equal our time. 8.33 times 8.33 times 100 equals 833. Divide that by 3413 equals 0.244. That equals 0.24. I'll just round it down in this particular case. So it takes 0.24 hours. How long is 2.24 hours? We've got 60 minutes in an hour. 60 times 0.24 equals 14.4 minutes. That's how long it should take to heat that 1 gallon of water, 100 degrees, with a 1 kilowatt heater element, or a 1 kilowatt propane burner, or a 1 kilowatt stovetop. So you understand that. See, that's as simple as it gets. We have reduced this down to something as simple as this. Let's continue to work through this. And the first thing I need to do is erase a little bit of stuff so that we can explain what we have and how we get to where we are. Because it flows all by itself. Now, there are certain things that we do know, okay? And now, when we're doing these measurements, let's reduce this down and explain exactly what that is. because understanding what that is really is what opens up this entire formula for you. We have volume in gallons times 8.33. And the reason we use 8.33 is because a gallon of water weighs 8.33 pounds. Right? Let me write it like this. 1 gallon H2O equals 8.33 pounds. Now, of course, this is all standard, all right? All right. What we do also know is we know that 1 gallon, I don't know if you knew this or not, of ethanol, and that's pure ethanol, weighs about 7 pounds. We already know this going in, that ethanol is lighter than water, and that's what causes a hydrometer to do it. You follow that. Okay, so there are some things that we have to accept going into using the formula, just to make things simple. We know that a mash is not 100% ethanol, nor is it 100% water. Now, for those who want to really geek out, oh yeah, you go ahead and you can take the percentage of alcohol and determine that based on its weight per gallon, and what the resulting or the remaining water based on weight per gallon. You could figure that out. But if we just make this as simple as we possibly can, we just use 8.33. We just use the weight of a gallon of water in our formula. It's going to give us within a minute or so of what we should anticipate. So we just negate that. So we got that. All right. Now, the amount, the measurement for heat transfer or energy necessary to heat is known as the BTU. And that's the British BTU, British Thermal Unit. And that's the amount of energy required to raise 1 gallon of water by 1 degree Fahrenheit. All right? This should start to come clear to you now. Things are starting to show up. We do know also, remember we went up 100 degrees on our example. Okay, we also know that, that's this part here. So that's what we're actually figuring out. But we're going to get, and we use that in pounds. And then we have the final temp minus the starting temp. Well, what is the temperature of your mash? I'm looking to get to, just as an example, I'm just looking to get to 175. Somewhere in that neighborhood, 174.8 or 3 or 173.8, it depends on which textbook you look at, is the vaporization point ethanol. So I'm looking to get at my final temperature, which is 175, and my starting temperature is, on average, around 75 degrees. You can figure this out depending on what your figures are. And that equals 100 degrees. So we call that a temperature change of 100 degrees. That's the delta. That's the difference. That's how much we want to raise. Remember, we're going to do... Now, we also know that, and that takes care of this part. This part is relatively simple because it's also a known factor. We know that 1 kilowatt equals 3413 BTUs. These things. Now, in actuality, it's 3412.14. So it's totally up to you. Look, I rounded up instead of rounded down, okay? So you can use 3.3412, or you can use, I just use 3413 because I've already crossed the threshold of the 12. So it just keeps all your numbers straight. So I've got 3,413 BTUs in 1 kilowatt. So far, so good. Yeah. So how many watts are in a kilowatt? Okay, 1 kilowatt equals 1,000 watts. Of course, we know what a watt is. All right. Now that brings us to, all we have to do is take this information, and we've worked that out. It translates into, because kilowatts are based on hours, kilowatt hours, and if we can determine how many BTUs are necessary based on our kilowatts to raise a certain amount of temperature in a certain volume of liquid, this being water ethanol mixture or just plain water, it tells us how much time it should take in order to get there. Let's erase some of this and do a few of these problems, and then you'll see where we're going with all of this. Okay, now, if we take that still again as an example, that's an 8-gallon still, and normally, I think we can all agree that we generally do about 5 gallons at a time. Of course, we're going to do a larger one, but we're going to do this one as just like going to be a 5-gallon fill. All right. So remember, we have 5 gallons of mash, and we're going to use our same data points, our same measurements of temperature. We're at 75. We want to get to 175. So we're going to change. We need a change of 100 degrees in Fahrenheit. And in this particular case, we're going to use a 2,000 watt element. All right. We'll use a 2,000 watt, or better known as a 2 kW, 2 kilowatt element. All right. So that's where we're at. Now we keep those things in mind. All we have to do is just place these into these formulas, and we can work out how much time it should take in order to heat that. Let's do it together. You ready? Okay, volume in gallons is 5. 5 times 8.33. 5 times 8.33 equals 4165 pounds. 41.65 pounds. We already know what our temperature differential is. We already know what that is. So it's going to be 41.65 pounds times 100 degrees Fahrenheit. And what should that equal? Times 100 equals 4,165. Equals 4,165. Now we have a 2,000 watt, better known as a 2 kilowatt element. Kilowatt times 3413. 2 kilowatts times 3413 equals, this equals 6,826, what are they? BTUs. That's how many British thermal units that we are going to have being inputted into our mixture. We divide the sum, the result here by that. And we come up with 4165 divided by 6,826 equals 0.61. That's 0.61 hours. At this point, it should be relatively simple. You've got 60 minutes in an hour. 0.61 hours is 60 times 0.61 because it's 61% of that hour. So 60 times 0.61 will give us minutes. 60 times 0.61 equals 36.6 minutes. Now what that tells us, this is the answer, as a matter of fact, right here, of what it should take. Now remember, that end result, this is the answer, 36.6 minutes, and to raise 5 gallons of mash or water by 100 degrees with a 2 kilowatt element, working at 100%. All right? Now, that negates the heat loss that we know that we are going to experience. All right? And that heat loss happens through convection. What takes place is every bit of energy that we're inputting into our still, at the same time that we're inputting energy and changing the temperature, we're losing energy at a substantial, not a substantial rate, but at a certain rate. That rate is going to be different with each and every individual still. That's just the way it is. You have a copper still is going to expel heat a lot quicker than a stainless steel still. As a matter of fact, stainless steel is 30 times more resistant to thermal transfer than copper. Glass is, oh my goodness, what glass is like 500 times more resistant than stainless or than copper. And air is in the thousands times more resistant in conducting thermal energy. All right? So we know that we're going to have those outside influences. We just don't know what they are. Yes, we could geek out crazy and try to figure this out because it all depends on the thickness, the type of material, the surface area, and the temperature gradient between inside and outside. That's just way, way too much for us to concern ourselves with. So what we'll do is we run this and we find out how long does it take. Not how long should it take. We find out how long does it take to get to 100 to raise 100 degrees. And when we achieve that, we jot that number down. You see where we're going now. Now we're starting to find out more and more about our system and about our particular still. And in this particular case, it took us an hour and 12 minutes with a 2,000 watt element. It took us 1 hour and 12 minutes. So that was 72 minutes. Now, if it took me 72 minutes and it should have only taken me 36 minutes, what can we determine from that? Well, we can determine what our efficiency rate is. How efficient is that system to withhold all of that heat that we want to control? Yes, we want to control that. So we take 36.6 minutes divided by 72 minutes equals, I'll rewrite this, 36.6 divided by 72 equals 0.508, which gives me an efficiency rating of about 50% for a 2,000 watt element. So that means that as I'm putting in, if I put in 2 BTUs, I'm losing one of them immediately. That is the rate at which I'm losing. And that's, I know that's a broad brushstroke, but that's what that tells us. I'm losing half of the energy that I'm putting in because I've only got a 50% efficiency rate or efficiency ratio. How do we increase that efficiency ratio? Well, there's a number of different things that you can do. First off is to insulate. And then if we insulate the kettle, of course, we're not losing energy as fast. Our efficiency rating should go up dramatically. Let's do another problem, all right? Because I happen to have, a lot of you have larger stills. I've got, as an example, I've got a 26 gallon. Let me erase this. And we'll erase that. And yeah, we'll erase this because these values are going to change. Now what will remain the same is I'm going to go from the same temperature gradient, okay, from 75 to 175. So I got a 100 degree delta. That's the difference in temperature from start to finish. But in this particular case, I've got 26 gallons. A 26 gallon still. And my temperature is 100 degrees is what my change, the change that I want to achieve. And I'll have a 5,500 watt element. So that's 5.5 kilowatts. Let's do the math. So 26 times 8.33 equals 216.58 pounds. That's how much my still is going to weigh now, additionally from its tar weight. We multiply that by 100, which is our temperature difference, times 100. That equals, I should be able to do this off the top of my head. That equals 21658. Okay, that's how many BTUs I need. Okay, that's how many, that's how many BTUs I need, because I can raise 1 pound with 1 BTU, but I want to try to raise this many pounds by that many degrees. Boom, 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 boom. See how easily it is to get tongue twisted and moved around. All right, now if I take this one and I'll divide that by, what was my kilowatts? My kilowatts was 5.5 times 3413. What does that equal? 5.5 times 3413 equals 18771.5 BTUs. That's how many BTUs that I can input. So if I take 21658 and divide that by 18771.5, that's going to equal the time. Let's do that. 21658 divided by 18771.5 equals 1 hour, 1.15 hours. What is 1.15 hours? Well, 60 times 0.15 will give us that minutes. That's 9 minutes. So this equals 9 minutes. This equals 60 minutes. When I add those together, that should take a total of 69 minutes to heat 26 gallons with a 5,500 watt element at 100% power. Now remember, your heat loss through your process is going to be a fixed value. All right, meaning that, as an example, remember we said that we were putting in 2 BTUs and we were losing 1. If I put in 3 BTUs, I'm still only losing 1, but I've got twice as much power going in. So what does that do to the time? Of course, that's going to reduce the time. What that also does is that also allows me to maintain that temperature a little bit more smoothly. So let's erase this and do this. And if we go back to our figures and we recall that we remember the 1 pound by 100 degrees with 1 kilowatt. So that was 8.33 times 100 divided by 3413. And that gave us 0.24. And that was 0.24 hours. Okay? Which was what? 14.4 minutes. Let's write that up here. 14.4 minutes. All right. So if I use this example and I say, 1 pound of water raised 100 degrees with 1 kilowatt is going to take 0.24 or 14.4 minutes. Well, remember, that's 1 to 1s. All right. For every BTU, for every BTU I'm putting into my system, I'm losing a half a BTU to external influences or conditions. What happens if I increase my input? Well, your heat loss is going to be a fixed value. It has nothing to do primarily with what's going in. It's just that's how much heat you're losing. So that being a fixed value, because I'm not changing the thickness, I'm not changing the makeup, and I'm not changing the surface area, nor am I changing the temperature gradient between ambient and my system. That means that this loss is going to remain the same. It's a fixed rate. So if I increase something, then what happens to my result? Well, if I increase my power or my kilowatts or the number of BTUs that I'm putting in, and let's say, for instance, I go to a 2 kilowatt. Instead of a 1 kilowatt, I go to a 2 kilowatt, and that would be 2 times 3. Yeah, I got to keep doing this. 2 times 3, 2 times 3413 is, now this changes to 6826, and now if I increase by 1, which is double it, well then I half the time. This changes to 0.12 or 7.2 minutes. So you see, in that particular case, what happens is we're just reducing the amount of time it takes to heat that stuff up. Now, with that much energy, if I'm still only losing 1, but I'm putting in 2, or a half, but I'm putting in 2, I've doubled my input, and I've halved the time it takes. Well, that stands to reason that as we continue to think through this process, and I'm trying to control that environment, and I've got as much control as I can have, well, now I can use a 2,000 watt element and I can maintain temperature much more efficiently. What happens if I use a 3 kilowatt element, 3,000 watts? Well, the same thing happens. It starts to multiply. Now, there is a point where you have too much energy, so we have what's known as flash boiling, and we don't want that to take place. So just keep in mind that if you can determine your ratio, how much energy you're putting in compared to how much energy you're losing, that opens up the whole world of how efficient your system is and what size element you are comfortable with using, and then how much time it should take you compared to how much time it does take you to heat up your system. By now, this should be relatively simple for you, because remember, what are we doing? We've got weight times change in temperature divided by BTUs equals time. Now that is as simple as it possibly can get. Now, as promised, you know, remember we told you at the very beginning, we said that it doesn't really matter if you're using a propane burner, if you're using a stove, if you're using a cooktop heater, or whatever the case may be. You still have to deal with those external influences, but we can determine how long should it take based on how much energy you can put into it. An average cooktop stove is rated at about 10,000 BTUs, okay? And those are the British thermal units. So we did the same thing. Let's take, as an example, let's take that 5 gallons of mash again in an 8-gallon still. And we're going to put that on a stove of natural gas. And it's got 10,000 BTUs. Well, if we take 5 gallons, 5 times 8.33 equals 41.65 pounds, multiplied by our temperature difference of 100 degrees Fahrenheit, times 100 equals 41.65. And now, in this case, we're going to divide by our BTUs. Since we're not using an electric element, we don't have to convert the element into BTUs. We already know what the BTU rating is on high. It's 10,000. Divided by 10,000 BTUs equals 0.41 hours. All right, 0.4, okay, 60 times 0.41 equals, it should take 24.6 minutes to heat 5 gallons of water by 100 degrees using a stove. Okay? Now, what about your turkey fryer? I think those are rated somewhere around 35,000 BTUs. So if we use a turkey fryer with a propane, and remember, the propane, they're rated based on the size of the orifices, how many there are, and then the PSI, pounds per square inch, of that liquid petroleum or that liquid propane being forced through. And that's how they determine what the BTU rating is, or how much energy it can dissipate. And in this particular case, we'll use the same figures, but now we're going to divide that by 35,000 BTUs. And what does that? Oh, this gets so much easier. 4165 divided by 35,000 equals 0.119 at 0.12 minutes, or 0.12 hours. Okay, so 60 times 0.12 is 7.2 minutes. So it should take 7.2 minutes, if you're using a turkey fryer, to heat 5 gallons by 100 degrees. Now if you start at 50 degrees and you have to go to 175, how many degree difference? That's 125. So you just plug that figure into here as 125 degrees, because that's the temperature difference that you're looking for. What if you have 9 gallons? Well, start off with 9 times 8.13. What if you have a 65,000 BTU burner? Well, just plug in 65,000 BTUs, and that's going to give you your answer. Now remember, this always negates all of that heat, the potential heat loss. But also remember that if you know how long it should take, okay, and you divide that by how long it does take, that's going to tell you what your efficiency is. The percentage of efficiency of your system. So therefore, you'll have a data point and an understanding of your system completely from start to finish, because all you're trying to do, again, remember, is to do what? We're trying to control the amount of heat loss and where that takes place. That heat loss should take place at your condenser. Now, remember back when we mentioned also, we said that copper is a great thermal conductor. Well, that's why a lot of times you'll have the worm is made out of copper, because copper conducts thermal energy so efficiently over stainless steel that it's an excellent condenser. That's the only reason why copper, or the main reason why copper is used in condensers, is because of its thermal properties. And that's why stainless steel is such a good deal in the construction of a kettle and a column, because it does retain heat a lot better than copper does. Not to mention, it's a whole lot easier to maintain, it's a whole lot easier to clean, it doesn't corrode, etc., and all those other things. So it's one of them six of one, half dozen of the other, and really it all boils down to a personal choice. So understand that a copper still dissipates heat a lot faster than a stainless steel still. But then and that's what you don't want to happen in the very beginning. But when it comes to condensing, copper is a better condenser than a stainless steel condenser. So you keep those in mind, and that will help you in designing and building your own systems to be as efficient as they possibly can, so that you can do what? Yeah, we can control the heat. Happy distilling.